Hello, this is the first video of the Hyperbolic Functions Series 2 on inverse hyperbolic functions for OCR Pure Core Further Mathematics, and it introduces inverse hyperbolic functions. You may have already studied functions in A-level maths and be aware that the inverse of a function can be found by reflection in the line y equals x. So here we have a graph with the red curve showing y equals sinh x, where sinh x is equal to a half of e to the x minus e to the minus x. Thus, reflecting in the line y equals x gives us the inverse function as the blue curve. The notation we use for the inverse of the function sinh x is either y equals r sinh x or y equals sinh to the minus 1 of x. Note that the graph showing x equals f of y is a reflection of y equals f of x in the line y equals x, and this gives an algebraic method to find an expression for the inverse function. So if y equals the inverse of sinh x, in other words r sinh x or sinh to the minus 1 of x, then taking the sinh of both sides would give us sinh y equals x, which implies that x equals a half e to the y minus e to the minus y, using the definition we were given in the last series. Multiplying up by 2 and then by e to the y would give us 2x e to the y equals e to the 2y minus 1. We can write this as a quadratic in e to the y. Noting that e to the y squared is the same as e to the 2y. From this we could solve this quadratic by a number of methods. Here I'm going to complete the square. So e to the y minus x squared minus x squared minus 1 equaled 0, and then that leads, with a bit of rearranging, to e to the y equals x plus or minus the square root of x squared plus 1. To find y, then, we need to take the natural log of both sides, and this would give us that y equals natural log of x plus x squared plus 1. Remembering that this is what we started out to find. Now you may wonder why we haven't used the plus or minus that we had here in the solution for e to the y. But you will notice that if we had x minus the square root of x squared plus 1, that would be less than 0, and input y isn't defined for this root. Therefore, in this instance, we only have the one solution for the inverse function of sinh x. We would do a similar working for finding the inverse of cosh x, starting off with the definition for cosh x, which was given in the previous series. Then multiplied by 2 e to the y to form a quadratic in e to the y, which we then solved by completing the square to give us potentially two solutions. Taking the natural log of both sides, this would lead us to y equals the natural log of x plus the square root of x squared minus 1, or the natural log of x minus the square root of x squared minus 1. However, we would say that the inverse of cosh x is only this one root. Unlike sinh x and tanh x, which are one-to-one functions, and hence their inverse functions are defined over the whole domain, we note that we have to restrict the domain of cosh x to make the function one-to-one. Otherwise, as you can see in this graph here, the function would extend below and above the x-axis, and we need to exclude the negative part. Thus, although there are two solutions to cosh x equals k for k greater than 1, there is only one value for the r cosh k. In a similar way, we can show that r tanh x equals a half the natural log of 1 plus x over 1 minus x. Again, looking at the graphs, you can see that they are reflected in the line y equals x. And to see this in more detail, please look at the textbook for working, or try deriving it for yourselves. Note that there are asymptotes at x equals minus 1 and x equals 1, and relate this then to the asymptotes at y equal 1 and y equals minus 1. Here are the logarithmic forms for these inverse functions. It is worth noting the validity for the arc cosh, or cosh to the minus 1, x is greater than or equal to 1, and as we looked at in the previous graph, for tanh to the minus 1 x, it's only valid for x lying between minus 1 and 1. Here is an example of equation which we may solve by using the inverse functions. Firstly, we would divide through by 2 to give us that cosh x equals 3. We can then write that x equals cosh to the minus 1 of 3. And using this logarithmic version with x equals 3 in there, that would be the natural log of 3 plus square root of 9 minus 1. This would give us potentially two answers: the natural log of 3 plus root 8, or the natural log of 3 taking the negative square root of 8. We could sketch y equals cosh x, and you'll remember from previous videos that that has a minimum at 0, 1. And here is the line y equals 3. We could see that we would expect two solutions using the log laws. The natural log of, in effect now, the difference of two squares. So it does seem as if those two roots are the negative of each other, and that both of them are therefore valid solutions. Calculators may also find hyperbolic function inverses, but they may not be in exact forms. In the next video, we will differentiate the inverse hyperbolic functions.